code. But that's at the end of the talk. So accretion disks is a paradigm of accretion disk turbulence that goes back to 1991, and that is if you have a magnetized rotating shear flow with an angular momentum profile with a rotation profile that decreases outwards, then this is linearly unstable to the magneto-rotational instability. And that means that you just have some kind of seek field, and then this magneto-rotational instability will then lead to accretion, and it will also lead to amplification of the field by some kind of dynamo process. So there's two examples of what you can do. The pencil code, this is from last paper from this year. You can take a global disk. We're showing here the projected gas density just at an arbitrary time, and you see because of this MRI you get this nice turbulent flow. And what I have mostly been working with is actually these shearing box models. So I cut out a rotating box out of the disk, and you see in this case it's stratified. But even on top of the stratification, you see these kind of structures here because it's turbulent by the MRI. And the idea is that magneto-rotational turbulence should lead to accretion through Maxwell and Reynolds stresses. And of course, we want accretion disks to accrete because we observe them to accrete. So it's a very strong paradigm. But there is a problem, which this is an example of the pencil code. If you take zero net flux magnetic field to begin with, it means that you don't have any net vertical field, for example. So you can typically start with some kind of weak seek field, large-scale seek field, and then you can let the magneto-rotational instability amplify the field, and then somehow recreate a field so that the MRI lifts, for example, from the vertical field component, and the MRI and the turbulence created by the MRI somehow replenishes that vertical field so that there's some kind of dynamo accretion cycle. But that is a problem. This is just shown with the pencil code. If you take this shearing box simulation I showed before at increasing resolution, so 64 cube, 128 cube, 256 cube, and if you always keep the mesh Reynolds number constant, that means that you are decreasing your dissipation parameters accordingly all the time. You see, I'm showing here the Maxwell stress function time. It starts out being around 0.03, then it goes to 0.002, and 256 cube I could only run around 30 orbits, but there is still a trend to decrease the turbulent activity when you increase the resolution. So it's kind of an nasty thing. There's a bit of caution here that this is for non-stratified simulation, so there's no systematic helicity separation, and there's probably no large-scale dynamo going on. And I have to say, it's not been formally shown that this is the same for global simulations or for stratified simulations. But I think there was a very nice paper from last year by Sebastian Fuhrmann and John Popoloso. I like this plot a lot. So they were actually showing, I think this is just the magnetic field some component at some slide through the box. And this is for low resolution, medium resolution, high resolution. And what you see is that the typical correlation length scale of the field actually goes down with increasing resolution with no convergent hit size. I think it's clear that there's something wrong with this way of creating self-sustained turbulence, and I think there's a motivation to think about alternative sources for creating vertical field. If this is some kind of small-scale dynamo, which I find is very likely, then there are two issues. One is the resolution issue, and one is if the Prandtl number is less than 1, it becomes extremely difficult to excite. And in most accretion disks, we believe the Prandtl number to be pretty low. I think in protoplanetary disks it should even be like 10 to minus 6, but even in AGN disks, it should be relatively low, except for the very innermost part, right?
Yes.
I think in galaxy disks, the Prandtl number is high, right?
Yes.
But that's not an accretion disk as such, so that's not.
AGNs are mostly hard to.
Yeah.
Hard on low density.
Anyway, so what you and I have been thinking about is, okay, what if we begin with a strong azimuthal field which is in equipetition with the thermal pressure, and then what we're seeing is a whole different behavior of the MRI. So what we see is that the buoyancy and Parker stability become very important, and actually the Parker stability creates a vertical field so the azimuthal field becomes unstable to magnetic buoyancy to the Parker stability, so you get loops of magnetic field that also, so the azimuthal field then has a vertical component also, So the particle stability creates vertical field in a very transparent way. We actually know what's going on, whereas with the small scale dynamo, we don't. There's some vertical field being created, but it's not in a very transparent way. And once we have the vertical field, then we can see the MRI, and we can get very high accretion rates. I have shown that the stresses increase with increasing resolution, so we don't have the same resolution problem. And also quite interesting, I'll also show that the azimuthal field, even though it's lifted by the particle stability, it ultimately stays confined to the disk.
These are not direct simulations, right?
These are not direct simulations. No. These are hyperviscosity simulations. So our initial conditions is a shear sheet model of the Keplerian disk, and we use a linear vertical gravity going proportional to height over the midplane. And we initialize with a magnetohydrostatic equilibrium where the magnetic pressure is equal to the gas pressure. So you can solve for this equilibrium, and you get the density as some kind of Gaussian. And of course the By squared is some kind of Gaussian also, just with a different vector front. And the scale height is here given by so this is the usual scale height in case there was no magnetic field. C is divided by omega, but then we get this square root 1 plus beta to minus 1, where beta is the factor beta. So the magnetic field also props up the disk. So I'm just showing here a 2D rigid rotation. So I'll come back to the shearing sheet rotations. I just wanted to show what the particle stability does in itself. So of course particle stability goes back to work by Parker. And I'll just show.
It's Newcomb, 1961.
You're saying, yeah, okay, I didn't actually know that.
Parker does this.
Okay, so this is the Newcomb instability.
No, it's called the Parker instability, but Parker was referring to Newcomb, who has found it.
Okay. So what I've done here is I've just taken a 2D model now. So this is Y and this is Z, and this is just rigid rotation, and this plot is showing. The colors are showing density, and the full lines are showing magnetic field, and the dots are showing the arrows are showing the velocity field. And you see what?
The line?
Yeah, maybe you can turn all off.
No, I mean, here it's dark already in the front.
Is this helping? Or?
You see?
Is it very difficult to see? This must be a very bad projector somehow.
Well, it's sometimes dimming the light somewhat, so that it's sometimes bright and sometimes darker, the projector.
I don't know. You can turn on all the light if it's better.
Can we close the light?
Yeah, I guess we can. Okay, so what I'm showing here is basically the magnetic. So this is the time in orbit, and when you wait for a while, you see that the magnetic field rises in these arcs of a pretty long wavelength, typically 5-10 scale heights in the azimuthal direction. So you need a pretty big box in order to see this. And you see that the gas is actually then the gas cannot cause. Normally, gas is prevented from falling down due to magnetic pressure. But once these field lines rise, then the gas will fall along field lines. And you get pockets of gas forming here between in these valleys. Now it went brighter, right? I think suddenly it was brighter. You get these pockets of gas forming here, and then as gas vanishes from the tops, then the field lines get even more buoyant. And in the end, you get in this situation where you have like a few big arcs and then some mass density pockets in the midplane. And just show a movie also, I think. A movie. Yeah. So now we see the magnetic field rising, and then actually what happens now is that these arcs seem to merge and form these super arcs, and then eventually you go into this state, which is not really turbulent, it's just a transition from one state to another state. That's what typically happens in 2D rigid rotation. Yeah?
But you are using a alpha limiter there, right?
Yes.
So then, is it feasible that the field lines get so organized like that?
Yeah, it is. It is completely physical. It's not a turbulent state, as I said. It's a transition from this state to this state, which is energetically favored. There's no turbulence going on.
Okay, so then the question could be then, what is the influence of the alpha limiter?
In my experience, no.
No?
You can I think the upwind speed is set maximum here to 10 times the sound speed, and you can set it higher or lower, and I didn't see the bigger difference. But you programmed this tool. Do you have any experience that the upwind limiter can create something unphysical?
No,
You can always search for convergence by putting it up and up, and then seeing if the results change. But no, it's not due to the upwind limiter. I'm pretty sure about that.
May I ask, how these arcs knows where to enter actually when are there any seeds of some instability in these anchoring points?
Yeah.
Why they are set this place exactly, or because at the beginning if it's constant always exists at the beginning.
You mean why do
Yeah.
I mean, I think the final stage is set. Of course, there's a balance between buoyancy and tension. So the tension is now dragging the field lines down, and buoyancy is trying to get it up. So it goes into some kind of balance between tension and buoyancy, and it's almost force-free also. It goes into some kind of force-free equilibrium. So. And I also don't quite know why these small arcs merge to become bigger arcs, but some people claim that this is more energetically favorable. I guess you can see that because the tension should go down, right? If I go from a small arc to a bigger arc, I will get less tension. So I kind of understand that the magnetic field wants to do that.
In the nonlinear, in the final stage that you showed in the animation, is that the nonlinear stage, or is it still growing exponentially?
It is a saturated state. Yeah.
It's nonlinear.
Yeah, it is.
And nonlinear saturation involves coupling or something like that?
So what?
The nonlinear saturation of the pattern stability involves nonlinear coupling between modes, or?
No, I guess you can. Yeah, it must be nonlinear. It must be a nonlinear state somehow, because you need the magnetic tension there to pull the magnetic field lines down, and some kind of buoyancy wants it. There's some kind of balance between tension and buoyancy, and that must be non-linear, right? But actually, this was just 2D, so I'm showing here 2D rigid rotation. That's what I showed before. So I'm going to hide over the midplane. I made sure this is the initial azimuthal field, and you see here I had 12 scale heights in the Z direction, and you got this kind of profile. And then I also tried 24 scale heights, which of course means you have a ridiculous range of densities of, I don't know, 20 orders of magnitude or something. And actually that means that the azimuthal flux escape from the midplane just a little bit more, but it never goes to zero. It always makes a transition to a saturated state. But what's very interesting is if you do this in 3D, this doesn't occur actually in 3D. So now I'm actually showing, so this is the initial field. I'm showing a function of time, what happens to the field function of height or midplane, and you see the field spreads out completely. So in 3D, this is different. And you see it in 3D, there's something that was showed by Kimeda in 1998, that when you get these oppositely directed field lines, because the Parker instability has a pretty high radial wave number, means you get field lines that are like this, and then just very close separation in radial direction is the other way. And this is prone to reconnection, and then the field reconnects, and it just spreads over the box, and eventually you just have constant magnetic field and only thermal stratification. Yeah. So there's a very big difference between 2D and 3D, also because 3D allows for the interchange instability. So there are two sides of the buoyancy. One is the Parker instability, and the other is the interchange instability.
You have a connection also in 3D.
Yeah, but I don't have in the radial direction because I only have YC. So if I had the next radial plane there, I would see a very large change in the magnetic field arcs. Yeah. Okay. And this is prone to reconnection. Once it reconnects, then the field can actually escape from the disk. You can say in this case I have perfect insulated boundary conditions, so it doesn't escape; it just spreads evenly. Yeah. So I just want to give some motivation for why you want to start even with a plasma beta of one field. I think you can argue that some disk might actually have a.
Excuse me. So the initial field is purely azimuthal and points in one direction and it has no kx dependency.
Yeah.
So So how does the KX dependence then look like when they reconnect? Is it weak and strong?
I can
Or
show
do they
you.
actually reverse? Okay.
I can show you for the shearing box at least what it looks like. Yeah. So one argument for why you might want to consider initially strongly magnetized disc is you have a disc that is fed by rose flow overflows. First of all, the material here might be pretty magnetized, and also during this phase of going into the disc, there will be strong shearing motions. So I think there's some motivation for not always starting with weak seed field, but actually starting with a strong seed field. And also if you look at ADN discs that are fed by molecular clouds, they may also be magnetized because we know molecular clouds often have a beta of 1 strength magnetization. So just to repeat, so what is the problems related to the MRI? Well, what is the source of the vertical magnetic field? Because the MRI needs a not too strong, not too weak vertical magnetic field. But of course we also have toroidal fields in there that will give some kind of transient instability. So just like purely as a azimuthal field, you can also get some kind of instability. But there is a problem with that is it has very short vertical wavelength. And I will show you a plot later. That's probably not what we're seeing. So this is now the shearing box. So 12 scale heights, 24 scale heights, 12 scale heights. And Toby, this is the vertical field inside of the box, and you can sense here that has some kind of radial variation on very short wavelengths, yeah? And this is actually, so really the field, yeah? The field really goes up, and then it goes down just, a fraction of a scale height later, yeah? So I'm showing here for the shearing box, and yeah, you see this is what we're seeing in the 2D plane. Also now it's 3D, so we also see the radial variation. This is a typical fingerprint of the Parker instability, and I can just show how it develops into a very strongly turbulent situation. So now you see the linear growth here, and now I'm changing the range of the plot now, and we go into nonlinear growth, and you see a very strong vertical field here. Yeah? And you really get into a strongly fluctuating turbulent state with strong vertical magnetic field. But you also see we're not running out of turbulence, it's just saturated. It's not like in the 3D rigid rotation case where everything just died out. It just keeps on being turbulent.
So now you have MRI plus Parker, yeah?
Yes. And presumably, if some of you are close can actually see that there is some high KC modes here in the very mid plane. So I think I have MRI in the azimuthal field also. So I probably have vertical field MRI, azimuthal field MRI, and Parker instability interacting. Yeah. So what I'm showing now here is as a function of height over the midplane, you can measure in the saturated state what is By, and it started out being this dotted line here. That's the initial By stratification, and in the end, there is some loss of By from the midplane, and By increases a little bit here away from the midplane due to magnetic buoyancy, but it never escaped out of the disk. It never spreads evenly. And I also tried to vary the size of the box from 6 to 9 scale height, and again, there's no apparent difference. This line here follows that blue full line almost completely. So it has nothing to do with being close to the boundaries or the field somehow artificially being kept in the box by the boundaries. And if you look at the RMS of the vertical field that is created, again here we have for 2 box sizes and 2 resolutions. This is low resolution, this is high resolution. You see that you're creating a significant vertical field, and that it stays there. It doesn't die out. And you can also measure now as a function of height over the midplane. You can measure the Maxwell stress. So this is from the mean field. So I first meaned over x and y, both bx and by. So you see there's some kind of mean field which is in the midplane actually producing a little bit of a positive stress, but here significant negative stresses, and then in the fluctuating field it's negative everywhere, and there's really strong accretion stresses produced by the MRI. So all in all we get an alpha value of about 0.1. And of course, what we're interested in is some kind of accretion rate. You kind of end up with depends on the turbulent viscosity, and you can try to calculate the turbulent viscosity from the Reynolds stress and from the Maxwell stress, and you can non-dimensionalize with sound speed and scale height and get the alpha value. And actually here you have a look at moderate resolution and high resolution, and you see that the alpha value goes from 0.06 to 0.1, so the alpha value really increases with increasing resolution. So I think this is a very nice behavior. I couldn't call it converged, unfortunately, but at least it goes in the direction of the more interesting result.
Anders, have you ever looked at the zero net flux runs with the same kind of viscosity and the resolution dependence there?
With hyperviscosity?
Yeah.
Yeah, it's the same
Same.
problem. Yeah. Absolutely the same problem. So
Okay, you mean it increases? The zero
No,
flux.
same problem as in zero net flux.
Actually, wasn't
with
this
ordinary?
there was that finite net flux?
the plot I showed,
This run, is it finite net flux in the y direction, or what did we have?
it has finite flux in the y direction, yes, but none in the vertical to begin with.
And the vertical flux is zero and conserved.
Yeah.
The horizontal one is actually not conserved, I thought. Or what do you have as boundary condition?
Perfect insulator.
So the perfect conductor or perfect or
It conserves the mean Bx and mean By.
this perfect conductor.
That's perfect conductor. I use AAS, I think. So the opposite of vertical field.
Yeah, perfect conductor.
Perfect conductor, yes. So the mean By cannot change in the box, but as you saw for the 3D rigid rotation, the mean By can of course spread all over the box if it wanted to. So that we didn't have any variation in the magnetic field. Yeah.
So for how long did you run the 5-foot cloud run?
For around 20 ohms.
So are you sure that it converted?
It's been converging at that point for 13 ohms. So I'm pretty sure that it does. But I think the only question is now, why didn't the azimuthal field just reconnect and just spread evenly over the box? Because if that happened, obviously this mechanism would turn off. And what I did now is that I measured the function of height over the midplane. I measured what is the contribution to the large-scale azimuthal field. And actually what you see, so I have the blue one is advection and compression. This one is the shear term, the omega dynamo. So the Keplerian shear is creating Vy on Vx, and this is the stretching term. And what you see is, I think as expected, that the advection and compression term is actually removing Vy from certain moderate heights and taking it to even higher heights. That's what I would call buoyancy. Taking the Vy a little bit away from the midplane and moving far away from the midplane. Yeah? But the reason why Vy doesn't fall is that this is in almost perfect balance with this term, which is from the Keplerian stretching term. Yeah? So it's like the buoyancy is sending the magnetic field up, but then the shear term is sending things down again. And the reason it can do that is, of course, only because there's a large-scale radial field. This is what I'm showing here. It's called height on this plane. It's called time. This is Bx, the radial field, and you see this very, very clear structure forming with a peak in the midplane, then two valleys, and then another peak and another peak here. So this peak is, of course, the one that is causing this, and this valley is here, and this, yeah. So it's because the radial field lands at this kind of structure, then the azimuthal field does not escape from the disk. Then the azimuthal field can stay confined. So the radial field, so what I want to say is that the azimuthal magnetic field is in a statistical balance, and there's no net loss to regions above the midplane. And actually, it's the Keplerian shear that replenishes the azimuthal field. And this radial field is actually created by the magnetic stretching. So as gas particles fall down the inclined field lines, so Parker showed that actually in 1992, something that Anders has been working a lot on.
The gas fall down.
Yeah, I think I can show. I think I can show it here. So you start with an azimuthal field line, yeah? Then this becomes buoyant and goes like that. That means the gas falls down here. As gas falls down, it piles up here and it vanishes from here and here. Yeah, that means at this point can get even more buoyant, and this point is dragged down to the midplane. But then because of the Coulomb force, then you get rotation. So around, because this will then rotate into the picture, and here you rotate out, you get this counterclockwise rotation about dense clumps. And actually, you can show that this is some kind of this leads to some kind of alpha dynamo process, whereby a net radial field is created. So by stretching the azimuthal field. Yeah. So it's kind of, but it's not convection. It's more like falling down. It's kind of the opposite.
So some kind of physical convection.
Yeah. So you get helicity in the gas falling towards the midplane.
Yeah, because the engine is gravity still.
Hmm?
You have also the same engines and physical convection. It's gravity. Gravity.
Yeah. But there must be a difference. I still see a difference in gas falling down or gas moving out, but eventually it does the same. And then once you have the Cordillera shear there, that means that the Bx is then turned back into By, and that prevents the loss of By. So I'm just showing here what is so I'm asking the question now. What is creating that structure as a function of height over the midplane? So I'm taking that structure, and then I'm saying, oh, okay, the induction equation for Bx has of course these three terms, and then I'm just trying to consider which of these three terms actually adding energy to the large scale Bx structure and which is extracting. And it turns out that the magnetic stretching term is the one adding energy to that structure, and that both advection and compression is actually removing energy out of that structure again. Yeah? So this is somehow connected to magnetic stretching, which again is some indication that it's connected to this alpha model.
Why is it so noisy?
Because it's turbulent, I guess. It's MRI turbulent, strongly turbulent and fluctuating. So it's not always, you have to average quite liberally in order to actually see this.
And you reach a saturated state of the MRI?
Yes, I do.
So the time is orbital time, right?
Yes.
Okay, so 30 orbits.
Yeah. It is saturated, definitely. And what I show in the paper also is actually a very nice correlation between I can try to correlate the fluctuating electromotoric force with the mean azimuthal field. There's a beautiful correlation exactly with the right signs. So I guess that's just the conclusion for this paper, which is hopefully to be accepted soon. We had a very nice referee report, and I guess the referee went on summer vacation afterwards. So this is just my sketch of what's going on. That we start with some kind of By, and by target stability you get some kind of BC, which creates MRI, which gets a high alpha value. The By in itself is unstable to azimuthal field MRI and creates MRI and high alpha values. And By creates Bx by this, what I would call a Parker dynamo, but of course Parker that has more than one dynamo. And by Cordillera stretching, Bx goes back and we create By. But hopefully this paper should appear on SOPH soon. I just wanted to end by talking a little bit about solid particles in the pencil code, because this is something that both Matt and Anders will be talking about after me. So the motivation why we want to have solids as particles in the pencil code is that you can treat either. So if you have gas and you have dust moving in the gas, so some kind of pressureless component, then you can treat the solids as a pressureless fluid, which I did for my master's thesis together with Axel. And of course you can represent the solids by a scalar density field and a vector velocity field, and then solve for some kind of equation of motion and a continuous equation, and you of course include these advection terms. But you can also treat particles as numerical particles, in which case we give each. You can treat the solids as numerical particles, in which case we give each particle a velocity vector vi and a space coordinate xi. And then instead of these two equations, we are of course solving again an equation of motion without the advection term, and then we are changing the position of the particle according to the velocity of the particle. And the question is, of course, when is it okay to use solids as a fluid, and when should one really store solids as particles? And I guess my way of distinguishing between those two is that you need some kind of mechanism for localizing the flow in order to treat something as a pressureless fluid. I mean, in order for the fluid approximation to hold, you really need to be able to define one velocity field at a given point. And here I'm just showing, maybe if we have some red dust grains that are all moving this way, we have this blue dust grain coming in there. And if this blue dust grain doesn't collide with the red ones, they're actually allowed to go in here and keep its velocity vector that way, then we cannot treat this as a fluid process. But actually, what we can maybe do that even if these guys don't collide, if we have a very strong friction force, that means that what is setting the velocity of these guys here is the friction with the gas, which we don't see, and when the blue guy moves in there, that will feel the same friction with the gas and will then move in the same way. So if we have a very strong friction force, of course we can treat solids as a fluid. But once we will get larger and larger solids that decouple slightly from the gas, then it's not okay to treat them as a fluid anymore. And actually something I've been working on together with Andrew is a way to not only have drag force, so of course the solids move through the gas and they feel some kind of drag force from the gas. But we don't just have drag force from the gas and solids, but also from the solids back onto the gas. And this must of course conserve momentum, so you can see here if this is the solid, if this is the velocity field of the solids, there is some kind of friction force proportional to the velocity difference between solids and gas, and with a negative sign. But if you want to conserve momentum, if you want to make sure that this is okay, then you need to add an opposite term in the equation of motion for the gas, just with a rho particle divided by rho gas here, so that you can satisfy this. And this is actually very simple. If you have dust as a fluid, you can just implement this and it works. But if the gas is a fluid and the dust are superparticles, then you have to be careful that this is done in the right way. And I'm just going to show, so generally our particle mesh drag force scheme is that first you want to add drag force onto the particles, and what you're saying is basically, well, we want to know the gas velocity at the position of the particle. So this is the position of particle I, want to know the gas velocity. So this is suitably averaged over by some interpolation over the nearest grid point. So this is what we do here. We're summing over the nearest grid point, so grid points j, and then we have some kind of interpolation function here, which is a function of the distance between the particle and the center of the grid point, and then times the velocity field at that grid point. So we have some kind of interpolation.
Anders, that's some kind of first order mean of density. Already of a pH, W1, something like pH. How do you call that? Yes, some kind of.
It's just some kind of mean over the.
Yeah, so that's the first order.
It could be anything. I can show on the next slide what it actually can be. I'm just showing here. This is the most general case. Could be over the 27,000 nearest grid point if you wanted to interpolate.
The distribution function, the W1, something like distribution function. It depends on the space, and then you take the mean of the velocity times. Then you take the mean by using the local velocity.
I would call it a weight function. It just gives a weight to each grid point, and of course the sum of the weights has to be 1. It just says, I have a particle here, where do I get my velocity from? Yeah. So then once you know the gas velocity at position xi, then it's easy to calculate the drag force on the particle, because you just say the drag force of particle I, minus 1 over the friction time, which of course hides all the physics of the particle and at what time it reacts onto the gas, and then you just take the velocity of particle I minus this interpolated gas velocity. And now comes the trick. If you want to conserve momentum, you somehow have to add this drag force back onto the gas also. And what we actually do is that we don't do this again. We take the drag force, and then we assign that, we give that back to the gas grid points again, just with the opposite sign. So we know what the drag force was on a particle, and then we just give it back. So this is a back reaction force we give from the gas to the gas from the particles in the nearby cells. So we say that the friction force on the gas is just that we assign the friction force on the particles again with some kind of weight function, which is a function of the distance between the particle and the grid cell, and then with some appropriate factor in front here, which means that we conserve momentum.
Do you need the same weight to conserve momentum at each point?
Yes, you probably need that. At least for self-gravity, this is true. It's not clear that it's for conserving momentum. It's no. For conserving momentum
at each grid point.
No. I mean, I could actually say I'm a particle here. I get my velocity field. I get my drag force from the nearby grid cells, and then I could add all my drag force back on a grid cell here, and that would still conserve momentum. It would be completely unphysical.
But not angular momentum. If you take the momentum from here and you put it back there, then you create it. You add angular momentum or remove it.
Why is that?
How can you? Well, that's how you add angular momentum to the system. You take something and you pull it like this, and momentum is conserved until the whole stuff starts spinning. The lever, you have a different lever.
Just like this.
Yeah, I see the point. So one should probably always use the same. I think that's a good reason for always using the same function here as here. Also for drag force.
Just make sure that you add the momentum in the same way as you remove it with the same weight.
Yeah, I would always do that anyway. But but the thing is, for self-gravity, there's another argument that you can have self-acceleration. If you have a particle close to a grid point, and then you map it to the grid, and you calculate you solve the Poisson equation, you find the gravitational acceleration, and give it back to the particle. If you don't use the same weight and assignment function, then the particle will move to the center of the grid point. So
that's the one that unfortunately only works on a Cartesian grid, right?
Yes. That's true. So I would say in general always use the same function here and here.
That's because the Poisson solver doesn't need a Cartesian.
No, the balance doesn't work out.
Yeah.
On and off.
So these particles of yours, how big are they compared to the fluid grid cells? Extremely small.
Extremely small. Much smaller. They don't have any physical extent.
And you will never run into a situation where you actually have large particles actually in the grid cell.
I have done that not in the fancy code. I've done that with a separate code. Then you can make collisions and so on. But that's a whole different.
Yeah, and also you need some volume fraction that is actually filled with the. You add something in the fluid equations.
Yeah, I've never actually done that. So I just wanted to show three common interpolation assignment functions. So of course this all goes back to the book by Hockney and Eastwood, which and probably all of it goes back to before they wrote their book, but of course today is much more comfortable to just quote them. So you basically have to decide, and the easiest one is the nearest grid point. That means if the particle is here, it's only interacting drag force with the nearest grid point. That means we're kind of representing the particle density as just some kind of delta function. And then there's the famous cloud itself, which is that if the particle is here, it's interacting with the four nearest grid points, not equally. Here it would be interacting mostly with this grid point and least with this one. But this is the same as treating the particle as some kind of constant density cube. So you're saying that the cube of influence of a particle. The way a particle interacts with the grid cell depends on the fraction of its cube that overlaps with the grid cell. Yeah. And then there's a triangular-shaped cloud with a little bit higher order. You start interacting with the. So this is in 2D. You start interacting with the 9 nearest grid points, and 3D would be the 27 nearest grid point. And that's the same as representing the particle as some kind of pyramid. And yeah, here's actually the point. It's important to use the same function for interpolation and assignment to avoid any kind of spurious subgrid acceleration. And now I should probably add to avoid not conserving angular momentum. I think that's a good point.
How many particles can you deal with?
I will show 20 million later. It's kind of the highest.
With which interpolation?
I always use this one.
This one?
It's a little bit expensive. So this one, yes, good point. Nice showing you. NDP, I think, is just crap. The particle covers with the nearest grid point. It's extremely fast, and the reason why I think it's crap is that you don't have any linear phase. You cannot represent any linear density per equation. You can only have, if you have 10 particles per grid cell, you can have 11. That's a 10% increase in density. You cannot look at any linear phase. That means you cannot check the code. You might have some nice linear solutions of how the particle density should evolve under some circumstances, and you can't check that with a DP. So I think it's complete crap, to be honest. Then there's the CIC, the cloud itself, that means the particle comes with the 8 nearest grid point. This is quite nice. It has the advantage that it's much faster than the triangular shaped cloud. It has the disadvantages that you need at least 2 particles per grid point. I've seen the effect that if you only have 1 particle per grid point, these particles are moving away from each other. You can suddenly get spurious dips in the density, in the assigned density. Whereas I like with the TSC, you can really map the linear growth. You can get the linear growth right even with 1 particle per grid point. What I'm showing here, which you might not be able to see, is actually I just have a box of 2 pi, then I have something like 20 particles. And what I've done in here is I've mapped the particle density with the TSC scheme, and it has an amplitude here of 10 to minus 6. I can make a particle density perturbation of 10 to minus 6, and that is that I put all the particles equidistantly, and then I move them slightly, just by 10 to minus 6 of a grid cell. You would never be able to see it with your eyes. Yeah? And then when I go in and map the density with TSC, it exactly captures the right amplitude. So it's quite an impressive scheme. So even though it's a bit faster than CIC, I think it's quite nice. Although for analysis purposes, I think you're going for the CIC because you have non-equidistant grid, right?
Yeah, and basically I think the thing we don't have to make it easy to TSC is not too big advantage for us.
So what?
I don't think it's a big advantage for us to use the TSC thing. It's not too crucial with these densities for us. We basically just want to track the point.
Exactly. I mean, you don't have the back reaction back to the gas or anything, right? And this is not important. Or
in some cases we need that as well.
Yeah.
But in most cases it's not important.
Yeah. So I'm using TSC, and it's expensive because you can see that each particle covers to the 27 nearest grid points. And that's also in the vertical. That's in all directions, so you're losing a bit of cache efficiency there as well. Also.
So it's obviously then 27 divided by 8, which is 3 times more expensive. 4 times.
It's 3 times more expensive, yes.
Yeah.
But it might be even more because you suddenly can move 2 grid points away in the vertical. No, it's always only 1 grid point away. Yeah, that's true.
And this is related also to the order of the finely different scheme, no? But when you're at the border and you want with TSC, what do you do when you need, for example, 4 points outside the domain and you have 3 points?
You always only need 1 goal cell. Because you're always closest to a physical grid point. If you're not closest to a physical grid point, then you will do boundary conditions and come to the other side. So the particle is always closest to a physical grid point, and even the TSC only needs 1 grid point away from there. So it just uses 1 goal cell. Is that what you asked? Okay. So what I like about the TSC scheme is that you can actually check it if you know a good instability, then you can check the evolution of that instability and then see if the code is solving correctly for that. And for the shearing sheet frame, there's a very nice instability, which is a streaming instability. This was derived by Yudin and Goodman in 2005. And the idea is that the gas in a protoplanetary disk does not move capillary, it moves a little bit subcapillary because there's a global pressure gradient. But the dust does not feel that pressure gradient. So there's a different dynamics for the gas and for the dust, which means that there's an equilibrium solution where the gas and the solids are streaming relative to each other. So the solids are moving a little bit faster than the gas in the phi direction, but the solids are also moving greatly inwards because they're feeling the headwind from the gas. On the other hand, the gas are moving a little bit, the gas is moving slower than the solids in the phi direction, and the gas is always also moving out because as the solids are falling in, they're giving their angular momentum to the gas, which is then moving out. And actually, it was shown by Yudin and Goodman that this radial drift flow of solids is linearly unstable. It's not a simple stability analysis. You need to linearize. You get an 8th order dispersion relation, and you need to play around with mathematics a lot over the ideal. But you can actually derive the unstable wave numbers, and you can derive the complex omega for each of those wave numbers, and then you can seed the pencil code with exactly that wave number and check that you get the right growth rate. And it's interesting that the instability gets its energy from the global pressure gradient, so it's not a Keplerian shear instability, it's because there's a global pressure gradient. So what we did, Andrew and I, was that we wanted to use this also to check the drag force scheme of the pencil code. So what we're seeing here is that we measure here the growth rate of different components, UH, UY, UC, rho gas, particle X, particle Y, particle C, particle density. And as a function of the number of grid points per wavelength, we're showing here so this is the actual growth rate of 0.4 with this line here. And with these lines here, we are showing 4 different kinds of scheme. We're doing like TSC and we're using kind of different kind of drag force schemes. And we're actually showing that if you are kind of above 8 grid points per wavelength, then you have a fairly good agreement between the analytical growth rate and the numerical growth rate. But even below 8 grid points per wavelength, there's that fall off. And the problem is when you map the gas velocity onto the grid, that this is diffusive in a way. If the gas velocity has a certain, if you map the gas velocity onto the particle, so the particle will always feel a smaller amplitude of the gas than it's actually supposed to, especially at a small scale. So if the gas has a small scale component like this, the particles will maybe think that the gas velocity is only half of what it actually is. So all these interpolation functions are associated with a certain error, with always some kind of reduced amplitude. Yeah, I just want to mention that these two-stream instabilities exist in some other form in plasma instability, in plasma physics as well. And actually, they also use these particle mesh methods. That was some in the paper. Are you a co-author of that? I don't know. By Åke and Jakob, where they use this PIC, which I guess is the same as the CIC, it's the cloud and cell scheme, right? To actually simulate these two-stream instabilities for plasmas.
So it's the intermediate scheme. So is that the intermediate scheme?
I don't know. I don't know.
No,
So
probably independent of this question.
So I just want to finish by also looking at the non-linear evolution of the streaming instability. This is now the radial direction of the disk, the vertical direction, and this is a co-moving box where we ignore vertical gravity to get this is exactly the background of the linear stability analysis. We just want to follow it into the non-linear phase. And in the beginning, we just had all these meter-sized particles moving radially this way, and you see here that the streaming instability is setting in after. So this is not an orbit. This is about after like 6 or 7 orbits, and you get these funny structures here. And then the streaming instability goes non-linear, and you get these dense clumps, and eventually these dense clumps merge and form larger clumps. Let me just finish by showing a movie of this. So this is the maximum number of particles went to 20 million particles, 128 cubed, running on 64 processors. I can just show a movie here. So now it's just constant density. Now you see the streaming instability is making some kind of structure. It's very axisymmetric, right? You see the particles are drifting this way because they're exchanging angular momentum with the gas. Now it's non-linear, and eventually these clumps will merge and start having really strong vertical motion also. But now we can trust this because we were checking the linear evolution and checking against the analytical theory, right? Yes, so this creates some pretty strong turbulence actually, which is comparable to the strength of MRI turbulence, but of course the alpha value is negative because, or not of course, but the alpha value is negative because it's not a Keplerian shear stability, it's reached from the global pressure gradient. So my point here is just that that the particle scheme has been tested. I think it's really nice to do these linear, to compare with some linear evolution that you know from the analytical theory, and then once you can trust your scheme, you can enjoy these kind of movies much more, I think. Yes, that's what I had to say.
So yes, this is perhaps one of the first times that this kind of this type of calculation has been done. Because, first of all, streaming, definitely, yeah. But even with fluid and dust, where is this done? Fluid and dust coupled gas dynamics.
I mean, they're doing it with the source code now also, but I don't think they ever managed to even parallelize it. So they're doing the one-way drag forces with the source code. Oh yeah,
Did it too, right?
Samian Partikova here from Leiden.
Who's that?
Samian Partikova, he's in Cambridge now. And he did, what did he do exactly?
Oh, he did small particles, but large particles too. Basically, modeling how the tensor particles move if you have a planet in the disk too.
So he did a 2D planet disk and then he put dust particles in there, different sizes.
Yeah, and Richard Nelson put particles also in turbulent disks. So Alex, it has been used, but not with so many particles like that. And most of the times they don't have the pack reaction.
They never had it. Samian had it for part of his thesis, I think.
Just for the fluid particles.
Yes, okay. Oh yeah, okay, that's a little bit different for me. So I think the difficult part is really, if you put particles in there to parallelize it. I mean, I don't think it's difficult, but I don't think anyone here would consider it to be difficult, but that scares people that we have to use MPI, right? And then the next thing is to do the back reaction properly if you want to have this.
Have you explored the limit when the gas approximation for the dust breaks down? Is there a regime where the two are very close?
My rule is that if the particle crashes because there's too strong density gradients in the dust, then you need to use particles.
Yeah, but the question is whether the results are any parameter regime actually equivalent? Or is there an overlap between the two regimes of validity?
I didn't check, but of course in the limit of small particles they should do the same basically. In the limit of small particles and strong friction force, they should behave the same. As I said, I think the pragmatic reason for me to go from a fluid to particles was of course the code was crashing. The code can't handle these kind of density gradients, so there's basically zero.
Yes.
And then jumping up to 1,000, then you will have to play with shock diffusion for the dust or something. So
yes.
but of course this is all physical because it's a pressureless system, so it can build up enormous density contrast.
Yeah, I mean, I was just thinking it would be nice to explore this transition, the smooth transition.
I mean, one thing we did, actually, you will notice on this plot, maybe this full line is actually for two fluid. So actually you can see that the fluid approach is much better at capturing the evolution of the streaming stability, even down to like 3 or 4 grid points per wavelength. Because that doesn't have the inherent
Noise.
diffusion. It's not so much noise, it's just that the amplitudes are, both the gas and the dust seem to underestimate each other. The dust thinks that the gas has a low velocity, and the gas thinks that the dust has a low velocity, and then everything gets a little bit underestimated on small scales. So maybe this is a nice test of the two regimes in comparison.
So what boundary conditions do you use in the stratified MRI, except from perfect conductor?
I actually found out that I use no slip, which means no vertical velocity, and the two other velocities are just don't have any derivative. But then what was very important was for the density I had to use S.
But that's stress free, right?
S? No, S means symmetric gradient. That's not compatible with stratification.
I use SSA.
Oh,
But that's,
For the
no
velocity.
slip is AAA, right?
What was it?
No slip would be AAA, I think, wouldn't it?
But
Well, no, you don't, because what you're talking about is free slip, because you don't have,
I'm
you
using
don't have
free slip.
vertical shear,
Yes.
so the thing doesn't exchange
I'm using free slip. I hope that's what I call it.
momentum with
Yeah,
it.
SSA.
yeah. But
S
then
is
what
this.
is for the density? You said S.
S. I put S for the density.
Yeah, but that's not compatible with stratification, of course.
It is when you're using A for the velocity. That means that you can't use any. You can't violate hydrodynamic.
Well, you want to, what I found is that if you have A on for the velocity field, you want to have
Hydrostatic.
hydrostatic equilibrium.
It doesn't
I think
work.
you tried that as well.
It doesn't work. Yeah. No, not for the because this is magnetohydrostatic. The magnetic field is a significant part of the stratification, right?
Yeah, okay, no, that's of course a problem, yes.
Yeah.
That's why it doesn't work so well with magnetic fields.
It
But it still should work better than nothing. I mean, no balance at all.
No balance at all gives no problem as long as you have A for the vertical field for the vertical velocity. That means even if you are losing balance at that exact point, it will never spread anymore because you always say velocity to be zero.
Okay, I find that surprising, but
That's in my experience. The worst thing I tried was to use for the density to use any kind of smooth extrapolation, like A2 or V3 or something. That was a complete disaster.
well, none of these make any physical sense.
I know, and it also means that if it means that if you have a little bit less density near the boundary, it will extrapolate to be much less outside. And then this would be dragged in by if you don't have hydrostatic equilibrium, the much less density outside. Then the density gets much lower, and you're extrapolating that to the ghost cells, which then say, oh, there's much less density outside. That's a complete disaster. I think the most stable thing I did was S, and the reason was also that you could even have the situation that density goes down and then it goes up at the last grid point, at the very last grid point. And if you extrapolate that smoothly, it might actually mean that the code thinks that there's a very high mass outside of the box. And then that falls down and comes into the box, so you get these strange pileups of mass.
Why would mass outside the box fall into the box if you have velocity zero?
I think it would be diffused into the box. As a matter of
You're
fact.
using mass diffusion.
I use shock diffusion.
Shock mass diffusion.
I had to.
Well, we have to because the boundary conditions.
No, I don't think. I really tried all boundary conditions I could, and I don't think.
Yeah, I mean it's a very
It's
difficult
because
problem, but I think.
I have a Mach number of around 5 or 10, just from physical reasons, gas falling down magnetic field lines. So I think I'm stuck with the mass diffusion, which is a complete disaster also, especially if you do logarithmic density, but do all kinds of unphysical things. So I can actually see that the mass diffusion would then diffuse in mass from outside the box. Then the density at the last grid point would increase even more. It would extrapolate it even more, and then suddenly you get this blob of gas just falling in and damaging the entire system. So.
In this connection, I could maybe ask whether anybody had ever had any positive experience with the density floor, or even with ceiling.
What?
Whether anybody had ever positive experience with the density floor or the ceiling.
I can postpone problems for a while with the density floor. But they always seem to come back just later.
Would you agree with that?
Yes, and it like. But I am not even if just to set limiting density in order to that in this tough time.
Are there any production results where it actually works?
And I would
not even
And I would claim the density gets very low because the diffusion operators are not very good at, especially for logarithmic density, the mass diffusion operator can actually extract mass from where the mass is already lowest. That's what I'm seeing sometimes. The density just plummets. It goes through a logarithmic space from 10 to minus 3 to 10 to minus 27.
What are you saying then? That it helps?
No, I'm saying that mass diffusion is causing that.
It's causing that. Yeah. And then, so what about my question about the density flaw?
Yeah, it can postpone the problem for a little while, but suddenly it gets bad.
So have you been? You never used that.
I tried it and I didn't find any significant improvement.
And Vladimir, are you using it or not?
Which one, sorry?
The density flaw.
Oh,
So then I think we should take it out.
Mm-hmm.
I mean, I felt a bit opposed actually when I saw that it was in the code because, first of all, it gives bad credibility to the code. I know from experience in the late 90s, which we did, that it just causes garbage. So I think we should take it out.
But I don't think it will cause credibility loss. It's my impression that other codes use this a lot.
Yeah, but then of course they have lost my credibility.
I think we should keep it and then write a warning in a comment where it's called, and then say this is very unphysical and should only be used for testing. Because you might use it for testing purposes.
But then we shouldn't rename it into something more special.
Well, why is hilarious density for
Density for underscore testing.
Yeah. So what was your?
But then why is test for worse than alpha limiters or like feedback
or even shock master?
Yeah, I've been limiters. We work. We have seen this. I was asking whether production runs where it works.
And I've seen some.
And I was asking a question: can man demonstrate that with a density flow one can do a convergence test, as you were saying you can do with your Alvin limiter? And the answer apparently was no. Or not? So when you have not been using it. Have you been using it?
I've been using it, but it didn't make any difference for me. My simulation would crash with zero density anyway at one point. It would just jump over the density.
You made it work anyway, or what?
It didn't work anyway. I think we should keep it. But if you really want to rename it, we call density flow.
Just have a look here.
Underscore test. Or density flow underscore testing.
Yes.
Or something. So really show that this is not something we recommend. And we shouldn't write about it in the manual, of course.
But it, of course, is automatically in the manual, I think.
Or with the...
How's that?
Wasn't that right? Is it automatic on your computer?
There's a lot. Oh, but this is... but there's flow also in other things that maybe mean something else, right?
I think I put in a few flaws, but they were only for testing. I would never publish anything with that, to be honest.
But it says, for example, maybe there's some other meaning here. And if, for example, particle underscore number as an underscore flaw, these are different things. Right?
No, that's a completely different.
Yes, and then these are also set flaw values.
OCC, the passive scalar has a flaw also, right? That must be you even, or was that me? It could have been me, because I used it for small dust particles.
Yes, and it's extremely interesting. I mean, I actually think it makes things really worse.
Yes, I think so too. But I think it should be an option if you want to test if it might give you a hint about what's wrong with the simulation.
Yeah, but I mean, even when I see this in the code, it seems like that wow, all of a sudden somebody made some sense out of this stuff.
Well,
now you're saying me a problem.
but it might be
from the code.
useful, actually, or not.
What?
I can conceive that it can be useful, say, if you have like like 3D is a stratified disk in cylindrical coordinates, right? Or so. So then there, the density in the inner part changes by like 10 orders of magnitude or more. So a limiter there, makes the code run actually.
So you say you can actually
That's
produce
a
production runs with it?
I didn't do it myself because I moved it to spherical coordinates. But it might be, that someone might want, by some reason, to actually run a stratified disk, or in Cartesian coordinates or in cylindrical ones. Then in this case, then the density floor will be needed. But then, you also have to shut down the physics there. So it's much simpler to actually move to spherical coordinates. So it can be used if you want to do some special thing.
Why don't we just write in the comment? We can even call density. We can even call the variable density floor underscore testing.
For testing.
Not only the logic, but even the variable we can call this. I think it's actually a good idea.
Yeah.
Okay. So I am Vlad Lyra, and I will be talking about how to form planets in turbulent disks. Working in this field in the 18th century was quite simple. The only thing you had to do was say, that planets are formed in disks of gas and dust, and it was all. So these three guys here mentioning that, but they never really explained how, you pass from micron-sized things to a Jupiter planet or so.
They probably knew it. They just didn't know it.
Exactly. Yeah, and Cambridge that too. So then we are left to explain the details. So then the most favorite hypothesis nowadays is the planetesimal hypothesis So basically means that the body grow progressively. So you form them meter-sized bodies by electrostatic forces that causes them to pass from this size to this size by staticking, which is a process that takes a long time, and Anders will be talking about that. And once you reach the kilometer size, then it's quite simple to grow further, because then you have gravity to add. So then they can gravitationally focus the other planetesimal tube. So then once you have these building blocks, they can merge to form rocky planets that if they have a critical mass, like say like 10 to 15 Earth masses, then they have enough gravitational pull to attract massive gaseous envelopes. But there is one major unanswered point here, is that how to pass from meter to kilometer, because well, this sticking doesn't work there, because they don't stick, they break, right? Gravity doesn't work either, because they don't have enough mass. And then also there's a time scale barrier, because these bodies are large enough to be loosely decoupled from the gas, but it still are small enough to suffer significant drag forces. So then they feel the headwind from the gaseous disk, and then migrate into the star in quite fast time case, like 1,000 years or so. So yeah, these are the three main problems, and we can solve them by these methods. If they break, if they meet too fast, then you can overcome this barrier by making them collide gently. If they don't have much mass individually, it can be that if you have high number densities, they can collectively have critical mass, and then the migrating problem can be overcome by some sort of a stopping mechanism. So then we are modeling that with the pencil code, and these are the equations which we are solving. So isentropic flows. Sometimes I do it isothermally too, which means gamma here equals 1. Well, we also have the drag forces, self-gravity, and then here it's seen better by this part here being the gas equations, the particle one here, and then this particle zone, you have a particle gas interaction. Like you have here, sorry,
what is rho P?
Rho P is the particle in internal density. Here the particle radius, right?
But I mean, if you look at the
Oh.
gravity potential, you have the particles individually contributing to the gravity field, and then you
Here,
have
right? Yeah. Oh,
no, further down. Then you,
sorry.
next to equation, and then you have rho P
Yeah, exactly.
as a source of this
Exactly.
line as
This is the bulk density of the solids. So you have your particles there, right? And you then map the particles to the grid. So you can draw a density value from this.
But the way you've written the two gravity potential equations, don't you count the particles twice?
No, why?
Because you have a rho p in the second equation on the right hand side, and you have the sum over the masses in the first equation. Aren't these the particles too?
No, okay, fine. So yeah, no, these are dust particles, and here massive particles, like say star, planets, or same particle too, as I will show later on.
But,
So then here,
but
yeah,
rho S, actually, there's S and P.
rho s squared,
It's G for gas.
G, gas,
okay.
yeah, gas,
The other
particles,
is P, yeah, for particles.
Yes.
And so that's really the, so it's not the density of the solid as such, because
No.
that would be 4 times 10 to the 3
That's here,
kilograms
actually,
per
yes.
cubic meter.
this is
So
the
it's not that.
density, no, exactly. Yeah. This is the internal density of a solid particle, and then here, the bulk density counting the empty spaces also.
Mm-hmm.
Yeah. That's the main point. Yeah, like, and then here it is dealt with the end particle.
In this equation, there's both viscous forces neglected and
Viscous forces, we only do it with hyper viscous forces actually.
Yeah, but they
We
will be
want
important.
to maximize, yeah, sure to do that.
So I don't think it's good to just not neglect it. Do you think you should then write?
Write it here.
Yeah.
Yeah, okay.
I mean, if you take the,
I can do that.
if you're in a steady state, U cross B, it will balance against something, which in this case would be 0.
U plus B here.
Yeah. So if you have a steady state,
Yeah.
even just on the average,
Okay.
it will have to balance against something, which in this case would be 0.
Mm-hmm.
Meaning
Well,
that-
yeah, we do have hyper resistivity there.
It's better to write it actually
Yeah.
down.
Okay.
And the same with the viscous heating, because otherwise you don't have energy conservation.
Next time I will do that.
Mhm.
Okay, so, so we are modeling that with the 3 coordinates systems here. We have models done in Cartesian grids, in cylindrical disks, spherical ones too. So if you want to model protoplanetary disks with the tensor code now, you have your set of choices there to pick from.
Does it make a significant difference?
Oh, yes, it
Is there a significant difference between cylindrical and spherical
Yeah.
once you just have such a narrow wedge anyway?
Yeah, that's what I was mentioning here, with
Talking
the,
about height.
yeah, exactly.
The wedge is in
That's
height.
what I was mentioning here with the density of force.
It changes a lot.
Yeah, if you want to model it
Okay.
in cylindrical coordinates,
Yes.
if you have here the density being 1, then the density here can be about minus 100. Well,
So the wedge sort of follows the
Phase
density
transportation,
angle,
exactly.
the content of the density
Yes.
roughly. Yeah.
And then, to pass them from meter to kilometer, we know that the solids are pressureless, so then they will always move towards the pressure gradient if you have a drag forces there, which is seen here from the equations. So W here is the velocity of the solid particles, here the gas particles. So if you solve here then for the terminal velocity, you see that it's always instantaneously pointing towards the pressure gradient. And then it was shown here by the Cooper, that if you have a spiral arm there in the disk, then the particles move towards it. And the same thing here is shown by Anders, that when you have turbulent flows, so then the gas gets overdense. This is the gas plot. Now we can then hear the test plot. This is in space, and then here in time. So you see here that when you have the gas being overdense, you also have the particles being overdense. So then one way to form a planets then is to have this pressure maximum being long-lived, and if you have self-gravity there too for the particles, then Anders showed that this step from meter size to a thing like series happens naturally, because the particles get caught in the gas over densities, where they reach very high number densities, and then undergo gravitational collapse. And the picture shown by Anders last year. Right? Let's skip. This thing should close. Okay, that's bad. Sorry? Really? Yeah, I think. Oh, right. Yeah, it made my computer crash now. So, sorry. Maybe.
To do an execute on
Oh, crap. Yeah, like it's naturally turbulent now. So.
Yeah.